Okay, thanks for the introduction. Good morning, I'm Sunggunan from KAIST. Today I'm going to talk about my research project about the text entry method for smart glasses, which is complementary use of eye gaze input and touch input modalities. This work is conducted with my advisor Ki-young Lee, and title of the paper is Gaze Assisted Typing for smart glasses. First of all, why smart glasses users will need efficient text entry methods? We expected that most typing tasks for the smartphone users will also can be requested to the smart glasses users, such as chatting with a friend, searching information on the web, and also entering a password for authentication. So, how smart glasses users should have to enter text? We first focused on the touch input modality, because touch input on the temple is one of the widely used input methods for the smart glasses. However, the temple on the glasses are not a common form factor. It has an oblong form factor, and so designing text entry method for it is quite challenging. Some researchers presented nice adaptations of text entry method for this uncommon form factor touchpad. One example is using a unistroke gestures. ULR designed 26 unistroke gestures for corresponding 26 alphabets. And another example is two-step touch gestures input. Because the touch input is too small to select a letter properly, Grossman et al. Split the input stage into two stages and presented swipe zone and swipe board techniques as the two-step touch typing method. Those are surely effective method on this kind of touchpad, but the limited input space of the temple makes touch gestures to be complex to use. Considering that the problem is on the complexity of touch gestures, iType can be a possible alternative for it. Popular iTyping method is dwelling method. To enter a key with a dwelling method, a user only have to look at the key for a while. It is a more simple operation than the unistroke gestures and two-step touch typing method. Considering that wearing position of the glasses, eye gaze is also a promising input modality for the smart glasses. In fact, wearable eye trackers already exist, such as Tobii Pro Glasses 2, and also HoloLens 2, which is high-fidelity mixed reality device, have been announced to provide eye gaze input modality. So, is the eye typing method can be an alternative for the touch typing on the temple? Eye typing may be easy to use if the eye tracker will track the user's eye in very accurately. However, considering both the display size of the smart glasses and the accuracy of eye tracker, the answer is questionable. The size of display will restrict the keyboard size and consequently restrict the target key size. As a result, if the eye tracker is not very accurate to select a small target, users will be suffered by out of control. And the second problem is eye fatigue. As you can see in the video, users tend to do not blink their eyes while doing eye typing, and it causes the eye fatigue. So, to address both the problems on the touch typing and eye typing, we present the gaze assisted typing method. It is a complementary combination of touch typing and eye typing. Gaze assisted typing, so-called GAT, is a kind of two-step input method. First, a user has to select one of the splitted sub-keyboards by looking at the key. And second, and lastly, the user should have to enter one of the keys in the selected sub-keyboards by doing one of the corresponding touch input gestures. Okay, let's see in step-by-step with our initial design. Initial GAT used 9 touch gestures and the keyboard split into the three sub-keyboards. First, user can select a sub-keyboard by looking at it. In this stage, the sub-keyboards simultaneously respond to user's eye movement. Next, for example, if a user wants to enter the key C, the user first look at the sub-keyboard, and then to enter the key, user have to touch on the touchpad. While the user's fingers is on the touchpad, the sub-keyboards do not respond to user's eye gaze position. Due to this feature, user can relatively freely move their eyes while conducting a touch gesture. And next, the user have to conduct bottom forward directional swipe gestures to enter the C, because the C is located on the bottom right from the center. All keys in the sub-keyboards are mapped to corresponding touch gestures based on its relative position from the center position. Finally, after user detaches the finger from the touchpad, the key is entered. So we designed the GAT considering the following goals: more easy to use than touch-only method, and more error durable than eye-only method, and also less eye fatigue than eye-only method. First, toward more easy to use typing method, we tested 3 different swipe gesture sets to use. The maximum number of touch gestures in our design is 9, including 4 diagonal swipe gestures and 2 vertical swipe gestures, and 2 horizontal swipe gestures and a tap gesture. In case of diagonal swipe gestures, it is known as the hard to use on the temple because of the narrow form factor. In our pilot study, also, vertical swipe gestures are hard to use as the same reason. So we made the GAT options to eliminate those hard to use touch gestures first. And next, toward more error durable from the eye tracker's inaccuracy, and also toward less eye fatiguing interface than eye-only method, we varied the number of split sub-keyboards. Due to the display size is limited, the number of division is directly affected to effective target size of the eye selection target. And large effective target size is more error durable than a small target sized one. In this section, we assumed that error durable interface may cause less eye fatigue because it required less visual attention to the users. In short, however, here is a trade-off between the options. To use more easy to use gesture, GAT3 is more easy to use, and GAT9 is more easy to use, and toward the more error durable interface and also less eye fatigue, GAT3 is more effective. So we conducted experiment 1 to figure out which option is best. Those 3 figures are the 3 options. GAT3 consisted 3 sub-keyboards and used 9 touch gestures, and GAT6 consisted 6 sub-keyboards and used 5 touch gestures, and GAT9 consisted 9 sub-keyboards and used 3 touch gestures. We used the within subject design to compare each of 3 GAT options, and also used the memorizing and transcription tasks with a commonly used phrase set. In our implementation, we used Google Glass to use touchpad on the temple, but this experiment was conducted in remote eye tracking environment rather than wearable environment in order to use properly reliable eye tracker. Consequently, glass contents were also provided on the remote monitor. As a result, however, there were no significant difference across the 3 options in terms of speed and accuracy. Try to figure out why the text entry speed were not very different across the options. We decomposed the key input time into 4 parts. And finally, we found that sub-keyword selection time and touch gesture completion time, which are the T1 and T4, were cancel each other out. So all 3 options show similar text entry speed. As a conclusion of experiment 1 is how, even if the performance were not different to each other, most of the qualitative measures indicate that GAT6 is best. But in this experiment, we placed the keys in alphabetic order because GAT6 is hard to make the layout as a familiar one, similar to the QWERTY layout. So considering layout familiarity will affect usability, we didn't select the GAT6 as the best one. Excluding GAT6, second preferred option is GAT9, so we concluded the GAT9 is best in this experiment. And finally, to prove the effectiveness of GAT compared to touch-only method and eye-only method, we conducted experiment 2. We choose swipe zone as a touch-only competitor and choose adjustable dwell time method as an eyes-only competitor because both were surely representable typing method for each categories. And also we use the same tasks as in experiment 1. And so this is the demonstration video for the G89 in this experiment. As you may know, user first select one of the 9 sub-keyboards with the user's eyes. Then the selected sub-keyboard is highlighted with blue borderline. Finally, user can enter a key with 3 touch gestures. And then this is the video for the swipe zone. Due to time constraints, I cannot explain in detail, but in short, user have to select one of the 9 sub-keyboards with 3 touch gestures. But instead, the user must have to distinguish the 3 distinguished touch input region on the temple. And so the users can select one of the 9 sub-keyboards. Then select one of the 3 keys with 2 horizontal swipe gestures and tap gestures after selecting the region. And finally, this is the adjustable dwell time method. To enter a key with dwelling method, a user only have to look at the keys for a while over the preset dwell time. The user also can adjust the preset dwell time as you want after the every end of the trials, as you can see in the video. And in experiment 2, we used the wearable head-on display, which also has built-in eye tracker. So the glass contents were provided on the head-on display, and we also used the Google Glass to use the touchpad. As a result of the experiment, GAT was fastest over each monomodal text entry methods. After the 24 trials, GAT can reach 11 WPM, and compared to touch-only method, it is 29% faster, and compared to eye-only method, it is 25% faster method. Yeah. Next, about the learnability. We asked participants to rate how the given technique is easy to learn in 5-point Likert scale, and the figure is cumulated ratings on the question. Red color means very negative rating, and blue color means very positive ratings. And the annotated numbers indicate average values. As a result, GAT was rated as more easy to learn than touch-only method. And next is for the preference. GAT was more preferred than eye-only method. And for the eye fatigue, GAT was more fatiguing than touch-only method, unfortunately, but less fatiguing than eye-only method. So we meet our goal, maybe. Finally, for the eyes-only method, 4 out of 12 participants severely suffered by inaccuracy of eye tracker. But for the GAT, none of them severely suffered by inaccuracy. So we concluded GAT was more error durable than eye-only method. So it's the conclusion and contribution. Our contribution is presenting the concept of gauge typing and show we can make synergy both in terms of performance and qualitative measures. GAT was fastest compared to the monomodal typing method, and GAT was more easy to learn than touch-only method. And also, GAT was preferred than eyes-only method and less fatiguing than eyes-only method. And GAT was more error durable than the eye-only method. However, it's the main limitation. The limitation is our experiments were conducted in the simulated environment. So in our next work, we will investigate the environmental validity utilizing eye trackable smart glasses to deal with the limitation. Thank you.
Questions? One and two. Thanks for your work. Jake Weber from the University of Washington. I'm a little concerned about seeing speed results with no error rates. I think that we are at a state of affairs where that should never happen. Yeah. So I might have missed it, but I think around slide 41, the results from the first experiment were just speed. Did you force people to have perfect accuracy, and that's why you're only reporting speed? Otherwise, I don't know how to evaluate speed without errors.
Oh, sorry, I can't hear about the last words. Please say.
Did you? What were the error rates, the text entry error rates that you saw in the results for the first experiment?
Yeah, it's right. Actually, we measured the error rate for the both of the experiments, but because of the time constraint, I exclude the results because there are no significant difference in error rate. So, but in case of the experiment 2, GAT show lowest error rate compared to the other methods, but that's significant in statistically.
One more quick question. I think he was first.
Have you thought about applying this to a word-based method instead of a letter-based method?
Oh, sorry. What method?
Words instead of letters.
Word.
In whole words, selecting whole words.
Yeah.
Instead of selecting letter by letter by letter.
Letter-wise. My approach is letter-wise input, and so your question is using to the word level gesture input. Yeah, like maybe.
I was.
Sorry, now tick sound is so. Okay.
Maybe you can discuss offline,
Sure.
just in the interest of time.
Yeah.
Yeah.
Sorry about that.
We need to. Okay, let's give him a big hand again.